This lecture is going to be on spherical coordinates. We're going to have 3 coordinates like usual since we're in space, we're in 3 dimensions. Rho will be the distance from the origin. Phi will be the angle from the positive z-axis. And theta will be the same as it was before when we did polar coordinates and cylindrical coordinates. So let me show you a picture. So rho again is the distance from the origin. So if this is our point, this will be rho, whatever this distance is. Phi is the angle from the positive z-axis. And theta, like usual, is this angle. So if I imagine this point, its shadow in the xy plane down here, I'm just looking at the angle this makes with the positive x-axis. So that'll be theta. Again, theta is the same thing as it was before. The rho is new, it's a distance from the origin, and phi is the angle from the positive z-axis and also new. Well, we talked about r representing the distance to the origin before, so let me clarify. So what are r and theta in this picture? Well, theta we know, again, it hasn't changed. And r was really looking at the same point down the xy plane. It was the distance to the origin. So in space, it's not the distance to the origin. R is, in fact, the distance to the z-axis. So r is actually the distance to the z-axis, same thing as the distance from here to here. So in the xy plane, it's the distance to the origin. And theta, again, is as it was before, this angle down here. So we should think of r as a distance to the z-axis and theta as the angle from the positive x-axis. But there is probably a better way even to think of theta. If I look at the zx plane and just the half with the positive x-axis, so I have half a plane there, how far do I have to turn that counterclockwise to get to the point in space? So if you turn that half plane counterclockwise and get to that point, the amount you have to turn it is the angle theta. Theta is always going to be between 0 and 2 pi, like before. I don't really have to use 2 pi because 2 pi would occur when you're on the positive x-axis. And on the positive x-axis, you also have theta equal to 0. So if you want a unique representation for theta and r, you can stick to theta being between 0 and 2 pi, but not equal to 2 pi. Phi is a little bit different here. We're always going to take phi between 0 and pi. And why is that? Well, the biggest angle you can make from the positive z-axis is when you're all the way down to negative z-axis. That angle is going to be pi. So the angle going from the positive z-axis and then going all the way around until you get to the negative z-axis, that's going to be pi. So phi is always between 0 and pi, and on the negative z-axis, phi equals pi. And it's worth maybe thinking about what would phi be if you're on the xy plane. So if you're on the xy plane, you're on a plane that's perpendicular to the z-axis, going through the origin, and so that angle from the positive z-axis is going to be pi halves. So phi is going to be pi halves in the xy plane. No matter what point you pick in the xy plane, the angle is going to be pi halves. At the origin, just like with theta before, it's not really perhaps defined. We can just take rho to be 0 there. We don't care what phi and theta are. Let's look at some conversion formulas. So if we want to know how to write, say, a point in spherical coordinates, if we know what it is in rectangular coordinates, say, or something like that, we want to get cylindrical coordinates as well in here. There's a good little picture to keep in mind for converting, and that's more or less the picture I had before. I have rho being the distance to the origin, phi the angle from the positive z-axis, r the distance to the z-axis, and z would be, as usual, the distance from here to the xy plane. the height of this point over the xy plane. So if you can remember this picture, it makes converting fairly easy. Rho is just the distance to the origin again. So if this is the point x, y, z, this is just going to be the square root of x squared plus y squared plus z squared. That would be the distance from x, y, z to the origin. Now, if we want to know something else, then we can look at this picture and say, for example, sine phi is the opposite side over the hypotenuse of this right triangle. So sine phi is r over rho. So I can get r by taking rho sine phi. So again, because sine phi is going to be the opposite side r over the hypotenuse rho. Similarly, I can look at cosine phi here. That's z over rho. And so z is going to be rho times the cosine of phi. Now, once you have what r is, then you can use that x is r cosine of theta, like it was in polar coordinates. I mean, this is the same r and this is the same theta. So x is r cosine of theta. Then I just go ahead to write it in spherical coordinates, replace the r with this. So x is r again cosine theta. So rho sine phi cosine theta. Y is r sine theta. And again, r is rho sine phi. So y is going to be rho sine phi sine theta. So this gives us a way of converting then between the different coordinate systems. And it's really all tied up into this one picture. So if you can remember this picture, it'll help you convert with spherical coordinates back and forth with the others. So let me do a couple of examples involving converting from coordinates between coordinate systems. So suppose we know that xyz is 1, 1, 0, and we want to convert to cylindrical and spherical coordinates. Well, one thing that's important to know is how do we write these in different coordinate systems? And cylindrical coordinates, we're going to write r theta z, and in spherical coordinates, we're going to write rho theta phi. Now, I have seen some books do rho phi theta, so both of those occur in books. This one, to me, seems to be the most common, the rho theta phi, and that's what we're going to use. So let's look at this point. If I want to write this in cylindrical coordinates, r is going to be square root of 2. That's just the x squared plus y squared, and take the square root. Keep in mind, this is really just a point in the xy plane because z is 0. So we're just at 1, 1 in the xy plane. R is the square root of 2 there. What about theta? Well, if you're at 1, 1 in the xy plane, theta there is pi fourths. Z isn't going to change from what it is up above. It's 0. This says z equals 0. So that's where that's coming from. So I've written this point in cylindrical coordinates. Let's deal with spherical coordinates. Z is 0, and so we're in the xy plane again, and the distance to the origin will be the same thing as r. So rho is just going to be square root of 2. You can also use that rho is the square root of x squared plus y squared plus z squared, and you'll get the square root of 2. Theta hasn't changed, so it's still pi fourths. Theta is always going to be the same, regardless of the coordinate system you're using. What about phi? Well, as I mentioned, you're in the xy plane, so you're at 1, 1 in the xy plane. If you go from 1, 1 to the origin and then up the z-axis, that angle is going to be pi halves. And that's what the angle phi is. So this is pi halves. So that's rho theta phi. So we have r theta z is square root of 2 pi fourths 0, and rho theta phi is square root of 2 pi fourths pi halves. So that's our conversion for that. Let me change my point. And maybe I'll write in a different color here. So r theta z, r is still square root of 2. x squared plus y squared will be 2. Notice we're still in the xy plane as well. Theta is going to be, well, now we have pi fourths sort of, but we're in the third quadrant, minus 1 in the xy plane. And so it's really pi plus pi fourths. So that's 5 pi over 4. And z is still 0. Okay, so again, this 5 pi over 4 came from the minus 1, the xy plane would be in the third quadrant at an angle of pi fourths from the x-axis, so that's pi plus pi fourths, or 5 pi over 4. And the z just came from what it was up there. For spherical coordinates, again, it should be the same thing as r since we're in the xy plane, but you can square x, y, and z and add them and then take the square root, and you'll get square root of 2. Theta is always going to be the same. So theta in this problem was up at the top there in green. It was 5 pi over 4. Now phi. We're in the xy plane, so the angle is still pi halves. If you go from this point in the xy plane to the origin and up to z-axis, that angle will be pi halves. So that's what this looks like in this case. We have these 2 points, r theta z, rho theta phi, now converted from the xyz. Let me do one more example. And this example, we're not in the xy plane anymore, so it could be a little bit more interesting. And let me use the, let's just use black here. Okay, so I want to be a little bit careful where I write this. Here, I'll put it up here. So this will be r theta z first, r. Well, we get r by taking x squared plus y squared. So 3 squared plus 4 squared, that's 25. And we want to take the square root. So that's going to be 5. Now we want to figure out the angle here, what theta is. A tangent of theta will be 4 over 3. We're at the point 3, 4 when we put the shadow of this in the xy plane. So we're in the first quadrant. Tangent's going to be 4/3, tangent of theta. And since we're in the first quadrant, it will be the arctangent of that. So we are going to get the arctangent of 4/3. Z again hasn't changed. We had z was minus 12 here. It's going to be minus 12 here. Okay. Now for rho theta phi, I'm going to get, I want to take the sums of these squares. This one, when this one was already 25 when I squared them and added them. Now I want to add 144. And 25 and 144 is 169. The square root of that is 13. So rho is going to be 13. Next, we want to calculate theta. That's the same theta we had before. It's going to be the arctangent of 4/3. Again, those are always going to be the same. Next, we need phi. So we want to figure out what phi is. So this is a good question. What do we use to figure out phi? And what we're going to use, and I encourage you to look at the tip I wrote in the solutions to the homework for the spherical coordinates, because there's a good tip there on why we're doing this, but we want to use the formula we have for z. Z, remember, is rho cosine of phi. So I know z is minus 12 in this problem. And so this is going to be, well, rho is 13. So far we figured that out. Cosine of phi. So the 13 just came from the fact that we figured out rho was 13. And z is coming from from here, the minus 12. So we can see now that the cosine of phi is minus 12/13ths, and that's what we're going to put down. Then over here, we're going to put down the arc cosine of minus 12/13. So that's the angle phi, the arc cosine of minus 12/13 coming from here. Now, typically I make the angles come out nice, and I say not to use inverse trig functions when you're writing down these answers, because there's some nice trig functions that you should know. These values you don't know, so you can't really do anything with these other than write them down like that. But this is then for the 0.34 minus 12. This is the cylindrical coordinates, and this one is the spherical coordinates. So we've converted those. Now let's talk about how you do volumes in spherical coordinates. So here's a picture, and rather than rectangular boxes, what we're going to have for spherical coordinates, well, we have this piece of a sector here like we did for polar coordinates, but we also have a sector side here on this side. And you might remember when we took the area down here that gave us the extra factor of an r that we had to do in order to get this area, and that's where we got the r dr d theta in cylindrical or polar coordinates. Well, here, because of this extra side here, you're also going to get an extra factor of rho. So when I'm doing the integration, I'm going to have really rho times r times d rho d phi d theta. And here you can see I wrote this down, but r isn't something we use in spherical coordinates, but you should remember what r was. R in spherical coordinates is rho sine phi. So really this is just the same thing as rho times r. R was rho sine phi, and we have an extra factor of rho, so this is rho times r. So we get the extra factor of r like we did before for the area of this base or this part of this box here, and the other extra factor of rho coming from a similar reason in this for the rho for this part of the sector here. Okay, so we get rho r times d rho d phi d theta, or in spherical coordinates rho squared sine phi d rho d phi d theta. And that's also true down here. This is just showing you that if I want to convert from rectangular coordinates when I'm integrating, I should replace the x, y, and z with what they're equal to in spherical coordinates. And you can look back, that's what we said they were equal to. And dv gets replaced with the rho squared sine phi d rho d phi d theta. So this dz, dy, dx, or dx, dy, dz, or some variation of that is going to be replaced with rho squared sine phi d rho d phi d theta. So that's how we're going to set up integrals using spherical coordinates. And again, dv here is rho squared sine phi d rho d phi d theta. Let me do some examples from a book here because the pictures were pretty well. They look nice. This book does do things in the reverse order. I would start with the outside, look at theta, and then phi, and then rho. It's going to do rho, and then phi, and then theta. But let's go ahead and look at this. The pictures will be good, and this will be self-explanatory. So we're going to have a eighth of a sphere here, just the sphere in the first octant, with the center at the origin, and the radius is rho sub 0. So what do you think happens with rho here? Well, rho is just going from the origin to the sphere, so it's going from 0 to rho sub 0. And so that's the first picture they show. That rho is going from 0 to rho sub 0. Next, we want to look at phi. Phi is the angle from the positive z-axis, and we're going all the way from the top here to the xy plane in this picture. So phi is going to go between 0 and pi halves. And now we want to imagine turning this around, starting at the xz plane. Theta goes from 0 there all the way to the yz plane, where theta is going to be pi halves. In the xy plane, You can think of just what we have down here in the shadow of this is this quarter of a circle. Theta starts out at 0 here and goes to pi halves. And so when we set this up, if we're integrating some function here, the dv becomes rho squared sine phi d rho d phi d theta, like always. And theta is going to go from 0 to pi halves, like we talked about here. Phi is going to go from 0 to pi halves as well. And then rho goes from the origin to the sphere, 0 to rho naught, or rho sub 0. So that's this picture. Let's go ahead and look at another one. So this is the volume between two spheres. It's not going to be a volume. We're going to integrate some f, say, but we want to integrate the solid that's between over the solid that's between two spheres. One of radius rho sub 1 and one of radius rho sub 2. So rho is just going to be going between rho 1 and rho 2. We're doing the solid between these two spheres. So rho goes from rho sub 1 to rho sub 2. So phi is going to go from the positive z-axis all the way down here to the negative z-axis. So it's going from 0 all the way to pi. And imagine this picture and moving it around the positive z-axis. It starts out over here on the xz plane, and you go all the way around. You're going to go from 0 to 2 pi. So theta varies from 0 to 2 pi. And again, you can see in the xy plane, you're just going to have a region between two circles, one of radius rho 1, one of radius rho 2, and phi is just going to go all the way around the origin in the xy plane, so it's going to go from 0 to 2 pi. So we have theta going from 0 to 2 pi, phi going from 0 to pi again, all the way from the positive z-axis to the negative z-axis, and rho going between the two spheres from rho 1 to rho 2. Here's a picture of a cone, and what you should get out of this is that if I take phi equal to phi naught, it's just going to be a cone. This picture here, the cone on the outside here. Phi is equal to phi naught everywhere on that cone because the angle there, even to here, is phi naught. So on that cone, phi is equal to phi naught. Rho is going from 0 to the sphere, so let's start with that. So again, rho is going from 0 to rho sub 0. And phi, again, is going to go from 0 to phi sub 0. And how much do you have to spin this around the z-axis? Well, it's going all the way around the z-axis. So theta is going to go from 0 to 2 pi. And our setup will be theta going from 0 to 2 pi, phi going from 0 to phi naught, phi sub 0, and rho going from 0 to rho sub 0. If we're between two cones, so one with the angle being phi 1, one with the angle being phi sub 2, then everything's pretty much the same. Rho is going to go from 0 to rho sub 0, because the top part here, again, is a sphere. And then phi is going between phi 1 and phi 2. So the smallest thing it is from the positive z-axis is going to be phi 1, and then we're going to phi 2 where it's as big as possible. And then finally, theta, again, you're going all the way around the z-axis, so theta goes from 0 to 2 pi. And when we set this up, theta goes from 0 to 2 pi, phi goes from phi 1 to phi 2, rho goes from 0 to rho sub 0. And as always, rho squared sine phi d rho d phi d theta. So the last one I want to do like this is where I have a cone and z equals a constant on top. Z is equal to a. So we don't have a sphere anymore. So we're not going always from 0 to a, because this will be bigger than a for rho. We're going from 0 to a when we're on the positive z-axis, but over here we're doing something different. So how would we write down what's happening with rho? Remember, rho is going to be on the inside, so its limits of integration can depend on phi and theta. And in fact, what you want to do is to think of what this top surface is, this z equals a, and what z is in spherical coordinates. Z is rho cosine of phi, so that would mean rho is a over cosine of phi. So again, if I take z and replace it with rho cosine of phi and set that equal to a, I divide by cosine of phi, and rho is going to be a over cosine of phi on this plane. And the book that I took this from writes this as a secant phi, because remember secant of phi is 1 over cosine of phi. So rho is going from 0 to a secant of phi. Or again, you can say rho is going from 0 to a over cosine of phi. And then phi is going from 0 to phi sub 0, like before. And theta, again, we're going all the way around the z-axis, so that goes from 0 to 2 pi. So the setup, theta goes from 0 to 2 pi, phi goes from 0 to phi sub 0, and rho goes from 0 to a over cosine of phi. Let me end with an example of a different sort. We're trying to integrate x squared, and we're over a solid E here, where E is bounded by 2 half spheres. This is a half of a sphere. Y is positive. So this is a sphere. If I rewrite this, it's y squared equals 9 minus x squared minus z squared. Bring these over, and you have x squared plus y squared plus z squared equals 9. So this is a sphere of radius 3, but it's only that part of the sphere where y is positive. So it's a sphere of radius 3 centered at the origin, and it's only the part where y is positive. And similarly, here we have a sphere of radius 4 centered at the origin, but we're only interested in that part of the sphere where y is positive. So we have 2 half spheres here. We're between these two, and on the side we have the xz plane where y equals 0. So this is the picture. So this part here is the xz plane where y equals 0, and then you're between two spheres. So this will be the smallest sphere on the inside of radius 3, and this will be the bigger sphere on the outside of radius 4. So we want to set this up as a triple integral in spherical coordinates. So how are we going to do that? So let's figure out what's happening to each of the variables. So again, I prefer to start on the outside with theta here. In the xy plane, you can see we're going to have 2 circles. If I just look at what's going on in the xy plane, one of radius 3 and one of radius 4, we're going from the positive x-axis to the negative x-axis with theta. We have a circle that's above the x-axis in the xy plane, and it's half of a circle. And so theta is going from 0 to pi. For phi, we're going from the positive z-axis all the way down to the negative z-axis for this solid. So it's going from 0 all the way down to pi. So z-axis, positive z-axis here to the negative z-axis. Phi is going from 0 to pi. And finally, we have rho. I start at the origin, I go outward. I want to know the first surface I hit and then the last surface I hit. So the first surface I hit is the sphere of radius 3, and the last surface in this solid would be the sphere of radius 4. So rho is going from 3 to 4. Here rho is 3, and here rho is 4, and we're going from 3 to 4. So to put this setup up here, I'm going to have theta again going from 0 to pi. Phi was going from 0 to pi, and rho was going from 3 to 4. X is rho sine phi cosine theta. Again, you can help remember what this is as thinking of this as r cosine of theta. And if you don't remember what r is, remember that this is really rho times r. So this rho squared sine phi, if you remember that, is rho times r. And so I have r is rho sine phi, and then I have the cosine of theta here, r cosine of theta for x. I want to square x, I'm putting a square there. And the dv is rho squared sine phi d rho d phi d theta. So that's the triple integral. That's the setup. We want to calculate this, but that's how we set it up. To calculate this, let me make some room. This is what we're trying to do. And the first thing I did was just to rewrite this. We have an extra row squared here. So with that row squared, I get a row to the fourth. I have a sine phi squared and a sine phi there. So that gives me sine cubed phi. And I just have a cosine squared theta. So I want to integrate these. I integrate rho first with respect to rho. And this is a constant. So I'm just integrating rho to the fourth. And I'm going to have rho to the fifth over 5, evaluated from rho being 3 to rho equals 4. So 4 to the fifth and minus 3 to the fifth, well, you might not know those. You can use your calculator on a test for this class. So we're going to have 2 to the fifth is 1,024. 3 to the fifth is 243. The difference is going to be 781. And this is over 5. And so we're going to get 781 over 5 times then this double integral. So I've gotten rid of one of the variables, rho, and let me go ahead and just put this double integral at the top and work on the next variable, which is phi here. We want to integrate with respect to phi. Cosine squared theta is a constant. So theta is not the same thing as this. This is a constant. Cosine squared theta is going to be a constant when I integrate with respect to phi. So all I'm really integrating is the sine cubed phi here. But how do you integrate sine cubed? Well, there's different ways of doing it, but probably the easiest way is to rewrite it as sine squared times sine, and then replace the sine squared phi with 1 minus cosine squared phi. So let me rewrite that. Sine cubed phi, I'm using one of the sine phi's here, and then I still have a sine squared that I'm rewriting as 1 minus cosine squared phi. So then we can integrate each of these separately. Again, this is a constant. If I want to integrate 1 times sine phi, that's just going to be minus cosine of phi. So I get a minus cosine of phi when I integrate 1 times sine phi. When I integrate minus cosine squared phi sine phi, well, think in terms of a u substitution. U equals cosine of phi. This will be u squared. U is cosine phi. Du will be minus sine phi d phi. So when I'm integrating this, it's really just going to be u squared du. So I'm going to get u cubed over 3, or cosine cubed phi over 3. So this ends up being, again, a minus cosine of phi for integrating 1 times sine phi. And for integrating minus cosine squared sine, I'm going to get u cubed over 3 cosine of cubed phi over 3. And I want to plug in 0 and pi and take the difference with pi being the first evaluation. So when I plug in pi, I get minus a negative 1, so that's 1. I get a minus 1 over 3. So we get 1 minus 1/3. That's 2/3. And I want to subtract what I get when I plug in 0. So what do I get when I plug in 0? I'm going to get minus 1 here, plus 1/3. So that's a minus 2/3. So I'm getting 2/3 when I plug in pi, minus a negative 2/3 when I plug in 0. And so I'm getting 2/3 plus 2/3, or 4/3 for this, evaluated from 0 to pi. So this gets replaced with 4/3, and I'm left with an integral of cosine squared theta d theta. So I took the 4/3 out, and so what I have so far is a 781 over 5 times this 4/3 times now an integral that just depends on theta. So let me go ahead and move this to the top and get rid of the stuff in between. Now I'm integrating cosine squared theta. We've had to do that before with polar coordinates and cylindrical coordinates. You replace the cosine squared theta with 1 plus a cosine of 2 theta, all divided by 2. I'm going to take the 2 on the bottom here out, so I have a 1/2 out here, and I'm just going to integrate 1 and cosine of 2 theta. When I integrate 1, I'll have theta. When I integrate cosine of 2 theta, you could do a substitution there, but it's just sine of 2 theta over 2. And you can see this by taking the derivative. You're going to get cosine of 2 theta times 2 over 2. So that's just going to be cosine of 2 theta when I take the derivative like I want. Again, this 2 is out here. So now I want to plug in pi and 0, but notice sine of 2 pi and sine of 0 are 0, so this doesn't even really come up. All I have is pi minus 0, or pi, when I evaluate this from 0 to pi. So I have pi minus 0, just pi here. So this becomes pi. I can cancel a 2 here, so I have 2 times 781 over 15, and I'll have a pi here. So that's going to give me 1562 pi over 15. So that's the value of this triple integral we started with. It's 1562 pi over 15. And that finishes this example and finishes this lecture.